my first slide. My name is Jaime Cisternas. My collaborators are Andres Concha and Paula Mellado. They work in a different university in Santiago, Chile. The title is Finding Non-Trivial Stable Equilibrium States in an Array of Magnetic Dipoles. So we use a very simple and cheap experimental setup. So we can order by mail these small magnets. They come in exactly the specifications that we want in terms of length, in terms of magnetic charge. And we can, for each magnet, we can attach an axis and we can make them rotate in a plane, in the same plane, using a support. And we can apply an external magnetic field and see how they interact and how they either orient with the magnetic field or they prefer an alignment with themselves. So there are many things that we can try, and depending on the shape and the geometry and the locations of these magnets, small magnets. I think it's the cheapest experiments that you can make. It's about $10, the whole thing. So in these experiments, the things that we can change, as I said, the location of the axis of the magnets. We can change the separation between them. As you can see, let's say 2a plus delta is the separation between the axes, when then delta is the closest distance that we can have between the two endpoints of the magnets. And there is no need to make any approximation. So in most magnetic textbooks, one can read about this dipolar approximation, taking some limits. But I think that that kind of presentation, that kind of limit, takes all the beauty away of the phenomena. There are many things that are visible only in the finite situation, not in the infinitesimal approximation. So there is this competition, this nice competition between alignment, perfect alignment. So magnets want to be oriented with each other in this head-to-tail configuration, north-south, north-south. But if you apply an external magnetic field, let's say in the vertical orientation, then they polarize. They all point in the same direction. So we have this competition. This experimental setup, you can see the coil. One can see the wide support, and then we can see the small magnets. These particular magnets were about 1 centimeter in length. And here one can see that the separation between the magnets is about the same size of the magnets themselves. And there is a mirror just to have a better visualization and better recording of the location of the magnets. The experimental part of this research was published a couple of years ago in Physical Review Letters. And what we found is that there is this hysteresis. There is a coexistence of stable configurations. So in the plot I'm presenting you, in the horizontal coordinate is the intensity of the magnetic field. The B, little b. B can either be positive or negative. So the field can be pointing up or it can be pointing down. And in the vertical coordinate, I'm plotting the vertical magnetization. Say My equal 1 means that the magnets are pointing in the same direction of the magnetic field, up. Well, there is a small plot here in the figure that you can see. So in the absence of magnetic field, all the magnets want to be oriented in the same orientation. This is a ferromagnet, as people want to say. And as the intensity of the magnetic field goes up, the magnets take a canted orientation. And at some value of the magnetic field, there is a transition to the full polarized state. And as we vary the magnetic field in the opposite direction, as it goes down, there is a transition by a different value. So there is an hysteresis. There is a range of values of the magnetic field where we observe this coexistence. But we also see other things. There are intermediate states. So in this figure, we are presenting experimental in blue and also theoretical results using the model. And in both, well, they don't agree perfectly, but one can see additional detail, additional structure that may mean something. There are additional steps, additional bifurcations. No? There are many things that we can try to explore using the model. For this particular plot, we were using 4 magnets, but we can get similar picture using more magnets or even less, say between 2 and 12 and higher values. So here in this plot, I'm showing many experiments using different numbers of magnets in a similar configuration, always in this linear array. And there are all these features that we want to understand. And we think that bifurcation theory can say something about the nature of these transitions, about the existence of unstable branches. So in experiments, we only see what is stable. But what about the unstable solutions? Do they have any meaning? Do they have any relevance? And what about non-trivial configurations or complex? I mean, in this particular experiments, first they only observed, I would say, trivial configuration, meaning that magnets were doing pretty much the same, all at the same time. They were either polarized, pointing up or down, or they were pointing sideways, but they were behaving in a coherent fashion. What about configurations where some of the magnets are pointing up and some of the magnets are pointing to the left? So this is what I would say non-trivial or complex. What about connections between these branches? What is the role of symmetries? So this is the model, the basic model for the magnets. The moment of inertia, the angular acceleration, and the torques. So for each 2 magnets, there are 4 torques, so interaction between these magnetic charges at the endpoints of the magnet. So this is a dumbbell model in the sense that we assume that all the magnetic charges are concentrated at the endpoints of these magnets. So there is an interaction between the magnets. There's this friction, and also this the effect of the external magnetic field. If we only focus on equilibrium configurations, we don't really care about inertia and the friction. Most of the things I'm going to say are static. In the end, if time permits, I will say something about dynamic configurations. There are many symmetries. One is that we can apply a global reflection. So if we switch left and right, we are not changing anything physical. So that's one symmetry. There is another symmetry. If we take each magnet individually and apply a reflection around the vertical axis, we get another equilibrium state, another solution of the equation with the same stability properties. And there is a third symmetry that if we reverse the field, if we change the sign of the applied external magnetic field, everything remains the same, basically. If we change B and then change north and south poles of the magnets, everything remains the same. So all these transformations respect the stability of the system. And they have a role that we'll show in a second. So we have a group of symmetry with these transformations. So the identity, the global reflection, the individual reflection, and the combination of the two. And this symmetry group can be decomposed in subgroups. If we take a theoretical book like Golubinsky and Schaeffer, for instance, we learn that all these groups and subgroups are connected. And these connections show the symmetry breaking bifurcations that one can expect in principle. Meaning that if we have an experimental setup and we are free to move many things, in principle, we can expect to see these transitions at some point. Well, in this case, this structure does not depend on n. So these subgroups are associated to configurations of reduced symmetry. There are some trivial states. There can be stable or unstable. So a state with all the magnets pointing up is always going to be a solution. Always going to be. And if the field is high enough, that solution is going to be stable. There are some other combinations that we can use that are also solutions, but they're not always stable. It will show up in a second. And what about configurations of magnets pointing in the same direction, aligned with themselves? Well, as you can see, some of them are going to be perfectly stable and some of them unstable. We can explore this numerically using a software like Otto. And here I'm showing in blue the stable and in red the unstable solutions, always changing the intensity of the magnetic field B. As before, I observed these polarized states for large values, the positive values of the magnetic field, and for negative values of the magnetic field. But in between, we see this stable branch of these canted states. And we have a pitchfork and a saddle node. And one can see here in the small figures what they mean in terms of the configuration of the actual magnets, how they look like in experiments. And here we understand better the connection between the branches and the role of symmetries. How can we observe these unstable branches? Well, there are some tricks that we can use. I'm not going to say many things about this, how these configurations can be achieved in experiments. We can try to break the symmetry. Let's say if we tilt the magnetic field or tilt the linear array of magnets, we can see how these branches unfold and they separate from each other. And the pitchfork bifurcations go away and they become saddle node bifurcations. We are breaking the clockwise, anti-clockwise symmetry. There are some hidden symmetries that we can also break. Let's say with using some more complex configurations, not just a linear array, but something like a curved array. There are many things that we have been trying to observe more exotical phenomena. So this is only with 3 magnets, So, and for a different value of delta, say changing a little bit the separation between them. So please, yeah, I will, let's say, if we look at the figure here in the right, in the upper right. So we have this polarized state with full symmetry. Full symmetry, a very simple configuration with all the magnets pointing up. So if we reduce intensity of the magnetic field, at some point we have this pitchfork bifurcation. At that point, a solution with a reduced symmetry exists. That is unstable, but at some point after a saddle node bifurcation, it becomes stable. But what about the second pitchfork bifurcation in the same branch? Well, there is another branch, unstable, but at some point there is a secondary bifurcation that is also symmetry breaking. And that shows the connection between the actual bifurcation figure that we can get, either in experiment or in the modeling, and the isotropy lattice that we find in in a textbook of group theory. So we can explore these figures and try to replicate the things that are predicted by group theory. We can go to higher number of magnets and see very complex figures, spaghetti of unstable branches. So most of the branches are unstable. And there are interesting things for n equals 5, 6, and beyond, because we see some solutions that show magnetic domains. So they can be interesting for applications, for devices, for storing information. We see domain walls, if you want to see. N equals 8. And there are more non-trivial, heterogeneous, stable solutions, even in the absence of magnetic field. And these configurations are now observed in experiments. So using this theoretical result, we can go back to the experiments and try to achieve the specific configurations. And it has been done. It can be done easily. So let me show you this overall picture of the phenomena. So as the separation between the magnets goes up, situation becomes boring in the sense that we only see a few configurations. But for very small separations, values of delta, we see a wealth of stable and unstable configuration. Let me show something that I discovered about basins of attraction. So trying to control the specific angles and then letting the system evolve. Where does it go? To each one of these stable configurations, in the case that we have more than one. Let's try to paint the space of initial configurations and try to see the boundaries, the structure of these basins of attractions. So the system doesn't need to be chaotic to show rich structure. Let's try to use 3 magnets and explore a region where there are more than 2 stable states. And we get interesting figures. Let's say using blue and red, I can plot, say, the vertical magnetization. In the figures up, red means that all the magnets are pointing up. In the associated figure down, say blue can mean all the magnets are pointing left, and red, all the magnets are pointing right. So we see some structure. I don't want to go into detail because of time, but if we change the other parameters, we can see all kinds of strange shapes that are actually quite amusing. Let's look at this one for n equals 5, only showing the vertical magnetization. So intense red means all dipoles are pointing up, and dark or black means that the dipoles are pointing in the horizontal direction. So all kinds of beautiful shapes. This is the same figure, but now plotting the horizontal magnetization. And we can try to use this concept of boundary basin entropy and see the effect of changing the friction. So the lower the friction, we get to see more complex boundaries, more fine-grained boundary between these basins of attractions. Good. So in the benefit of time, let's go to the conclusion. So using this bifurcation theory, we can predict many configurations. Most of them are going to be unstable, but they're very interesting, stable configurations with domains that can be explored and used. There are interesting transitions that can be understood using the group theory and symmetry breaking bifurcations. There are basins of attractions. And good. So thanks for your attention. I would be happy to answer questions. if there's any. Good. Let me answer the question. So what can be said about arrays in, say, a cube or other shape, not just in a linear array? Well, people, not just our group, but other people have been using these other configurations with more complex symmetries. That's the issue. So the more complex the figure, one can explore other symmetry groups and symmetry lattices. So more complex bifurcation phenomena. I can only tell you about a ring of magnets, and placing an external magnetic field right at the center. And we can see more interesting structures that forces us to really use a group theory. And then the number of magnets is very relevant. In the linear array, the number n, well, it's not that relevant in terms of the symmetry. I hope it answered your question. Good.